Hey, hello, welcome back, Calculus 2. I'm moving on. So far, I've been sort of talking about some of the stuff that we were discussing before the break. I'm moving on into section 9.3, where we have a couple more tests for series here. So there's an integral test for series, and there's a p-series test. These are two different things, both covered in section 9.3. I'll see if I can get to them here in this video. The integral test is this. And here's what it says. It says if f is positive, continuous, and decreasing, so you got to meet those requirements for x greater than or equal to -1, and an is equal to f of n, then this series an and this improper integral from 1 to infinity of f of x dx. So again, either both converge or both diverge. So that's the integral test. You can take a series, write it as an improper integral by writing the an as a function, and we worked on improper integrals back in section 8.8. So remember, these improper integrals either converged or diverged. If we got a finite answer, we would say it converged. If we got an infinite answer, we would say it diverged. So then you can, since the series and the improper integral do the same thing, you can make a conclusion about the series. So we'll try this one for an example. This is a famous series, by the way, this 1 over n. It's called the harmonic series. But so, you know, maybe I should make sure it meets the requirements. So for n greater than or equal to 1, is it positive? Is it continuous? It is. You know, it's discontinuous at 0, but greater than 1, it's continuous. Is it decreasing? Yes, it's decreasing. I mean, the idea is I would write an integral from 1 to infinity of 1 over x dx, and I would try to do this integral. This is an improper integral. We've done this one before. Technically, the way you do an improper integral, though, is you make it proper. You take the limit as a goes to infinity, and you have this bounds from 1 to a, and then you try to do the integral. Well, that's the natural log of x. So when I do the integral, it's the natural log of x, evaluated from 1 to a, with a limit out front as a goes to infinity. So here we go. We conclude by saying, here we are. I get the natural log of a when I evaluate this, minus the natural log of 1. By the way, the natural log of 1 happens to be 0. So the answer is the natural log of a, and you take the limit as a goes to infinity. And the natural log function, as a goes to infinity, the natural log function approaches infinity. So the answer is infinity. And if the answer is infinity, we say the improper integral diverges. Again, that was discussed back in section 8.8. The reason it was discussed is because we can use it here for the integral test to prove that this series diverges. Whatever the improper integral does, the series does. So I'm going to go over here and I'm going to say this diverges, the series diverges by the integral test. I'd like you to use that language. I'd like you to tell me what test you used. Even though I guess it's obvious you did an integral test, I'd like you to conclude here that this series diverges by the integral test. There's a lot more examples. Again, you have to take the series and rewrite it as an improper integral. So there's a lot of examples we could do. I want to just jump to the p-series here now, because after doing this one example, there's a whole set of these that they all look like this. 1 over n to the p power, as n goes from 1 to infinity. So if I had an n cubed or an n squared or an n to the 1/2, or any of these, I could do an integral test on, do an improper integral. When we studied improper integrals, we studied a lot that looked kind of like this, but now I'm calling this a p-series, and here's the result. Here, if you have one of these, the integral test proves it to you, but here's the conclusion. If p is less than or equal to 1, but less than 0, less than or equal to 1, but greater than 0, then the series diverges. If p is greater than 1, if p is greater than 1, that power, like a squared or cubed or 3/2 or anything greater than 1, the series converges. I mean, we can use that now as its own little test, the p-series test. But again, the proof of that would be go do an integral test on it, and you would, if you remember doing some improper integrals, you might have remembered these ideas. Let's do an example of a couple p-series here then. I'm going to erase this and keep talking here a second. So this is easy. P-series is easy. You just got to memorize those rules. Let's try one here. If I have 1 over n squared, as n goes from 1 to infinity, that's an example of a p-series. If I have 1 over n to the 1/2, as n goes from 1 to infinity, that's an example of a p-series. And according to the rules, if p is less than or equal to 1, it diverges. So I'm going to look at this right here. P is, this is a p-series, and it diverges. I'm going to say p is 1/2. It's less than or equal to 1. I'm going to call it a p-series, and I'm showing my work. This is my work. These are my thoughts, and I'm finished. What about this one? Oh, hey, it's a p-series. Yeah, it's a p-series. I should communicate that to my teacher. P is 2. Sorry. P is 2. When p is greater than 1, it converges. It's greater than 1, it converges. So, p-series are easy. How can you make it more complicated? You can make it a little more complicated. Here's one. Let's see here. The cube root of n to the 5th over n squared as n goes from 1 to infinity. So maybe you can tell. That looks like a mess, and right now maybe it doesn't look like a p-series, but if you do a little algebra, it is a p-series. It's, let's see, what is this? This is n to the 5/3. Is that right? That is right. Over n squared. If I subtract exponents, I get a 6/3, and I subtract that 5/3. I'm left with n to the 1/3 in the denominator. Yeah, that's what it is. And that's a p-series, but it diverges. P is less than or equal to 1. The series diverges. It's a p-series. And p is 1/3. It's less than or equal to 1. It diverges. What's interesting is the limit of these as n goes to infinity is 0. The limit as n goes to infinity is 0. The limit as n goes to infinity is 0. The limit as n goes to infinity is 0. And we learned that when the limit is not 0, that's the nth term test that tells us it definitely diverges. And when the limit is 0, a lot of those converge. But a lot of them don't approach 0 fast enough. Some don't converge. And we're looking at several examples here. This guy approaches 0, but not fast enough to converge. This one does. This one approaches 0, but not fast enough to converge. It diverges. So the p-series proves it to us. And the proof of the p-series is the integral test. So that's section 9.3. Plenty of examples, a lot of good homework you could do. So thank you for watching. Keep working hard.